Okay, so many of these optimization problems are, the calculus part of this is usually pretty straightforward. The harder part often is just how do I set up the problem. Okay, so this is an ellipse. Okay, we have 6 and 6 here, and 4, 2 and -2. Okay, so we've got an ellipse. Okay, it looks like this, and we want to inscribe a rectangle inside this. Okay, we want the largest rectangle. I'm going to kind of assume it's probably longer horizontally than it is vertically. So I want to maximize the area of this rectangle. So I need to come up with an equation to maximize the area of this rectangle. So I'm just going to choose a point on the circle because the circle is what defines the positions of that corner. And I'm going to say that that's just x and y of that equation. And I'm just going to say that 4 times xy, okay, is the area of this whole rectangular region I'm trying to maximize. Now, I really should just kind of get rid of one of these variables, make it easier on myself. So I have a relationship here. How are x and y related? Well, if I solve for y here, I end up with y squared over 4 is equal to 1 minus. I can actually just get rid of this y and just do it all in terms of x, and then I can differentiate with respect to x. So working this out, I get y equals plus minus the square root of 4 minus x squared over 4 over 36 is 1 over 9. So I'm just going to use a positive version of that, and I've now come up with my equation. Okay, it's 4 minus x squared over 9. And I can now, I've got an equation in terms of x. If I find the maximum of that by differentiating, I can solve the problem. So a is equal to, I'm just going to do our product rule. And I'll factor that 4 out. X times 1 over 2 square root 4 minus x squared over 9. Just make sure that you can see that a little bit better. X squared over 9 times the derivative of negative x squared over 9 is going to be negative 2x over 9. Okay, so some things cancel out here. Okay, and then I'm going to solve this. So keep that 4 factored. That's going to be minus minus 2x squared. Oh, sorry, minus x squared over 9 root 4 minus x squared over 9. Okay, so I'm going to get rid of that multiply, or I'm going to get a common denominator here. So I end up with 9 times, well, I'm going to multiply that by its square root, so I'm going to get rid of the square roots here. Minus x squared, and that's all over 9 root 4 minus x squared over 9. Okay, now I can just solve this. We can simplify that. We're going to get rid of that 9 there. But I can solve this. I want to find out where we have a max. I want to know where that equation is equal to 0. I just have to worry about the numerator, and I don't need to worry about that 4, but I'm going to multiply that through. So I get 36 minus 9x squared minus x squared equals 0. So this ends up being, just make sure I got my signs all right. That looks okay. So I'm going to get x squared is equal to 3.6. When I solve that, x is equal to plus minus square root of 3.6. Okay, and that's, oh, I don't know what that is. Okay. So that's the x value. That's going to give us the max. Plugging that back in to here, we're going to get the y value is going to be, actually we don't need the y because I think we've written the equation in terms of x. So find the max area. Okay, so I'm going to just find the area when x is 3.6 square root. Okay, so I end up with 4 times root 3.6 times 3.6 divided by 9. I get the square root of 3.6. So I end up with, what is that going to be? So 3.6 times 4. The max area I'm getting is 7.6 units squared. Okay, so that's the max area. Again, I found the relationship. I made it, this time I had to use the other relationship to make this all in terms of one variable. I'm differentiating with respect to x to find the maximum of this area. Okay, so I make it equal to 0 and then solve.